Right now, from the Room to Room Weather Center, here's Mississippi's Chief Meteorologist, Matt Lobhon.
Well, hey there, I'm coming to you live from Red Bay. They're announcing me here. We're doing a school talk here at Red Bay Elementary for all the folks. And so I figured give y'all a chance to go ahead and catch up on it with us and watch it if you so like. Hopefully you find it interesting. I'm trying to do more and more of these school visits. Calendar's fairly full, I'll tell you right now. But if you'd like us to come on by, you can send us an email, info@msliveweather.com. Oh man, I have a hard time when you do the introduction. Uh, but yeah, we'll have it for you here in just a second. So, give us a moment. Okay, give it a second, almost there. And I'll try not to blur with this too badly. Thank you so much. Appreciate it. How y'all doing today? Awesome. Well, we have you live on our 24/7 Weather Channel right now as we're going to do this talk on there. So go and wave, everybody. Get everybody good and riled up before we try to get everybody quieted down so we can talk. But thank you so much for having me come out and talk with you guys here in Red Bay today. As of course, it's been kind of a wild year for us. But how many of y'all are excited to learn about the weather? Great. That's awesome to hear. Okay, so as she mentioned, my name is Matt Lopon. I'm the chief meteorologist for Mississippi Live Weather out of Tupelo, and obviously we cover y'all here in Red Bay as well. Usually try to make it up one time a year to the water park if we can. How many of y'all like the water park here in town? Yes. Yes. Okay, so I need to know the answer. Is it the fast slide or the other slide? Which one? How many of y'all like the fast slide? Fast? Okay. How many of you like the other slide? I mean, I like them both personally because we don't have any of those down there in Tupelo, believe it or not. So that's one of those things that y'all have that we don't. That we just absolutely love. So thank you so much again for having me come and talk with you guys today. So I'm a meteorologist, and a meteorologist is a person who forecasts the weather. And in order to be a meteorologist, you have to like or at least see on the speaking terms with three different things. Number one, you have to like math. How many of y'all like math? Yes, 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 yes. So many. That's awesome. That's a good sign that your teachers are doing a great job. Okay, put your hands down. Okay, now this exercise requires your teacher's participation for just a moment here. Okay, so teachers, I want you to take both your hands and put them in the air like this. Teachers, okay, okay. And then we're going to take those hands, ready? And we're going to do this with them right over our eyes. Ready, teachers? Okay, right over the eyes. No, no, not, yeah. Okay, I should do it. Okay. How many of you don't like math? Out of curiosity, okay? Put your hands down, down. Put your hands down. Put your hands down. Okay, so there was one person that ran out of the room. That's the only one that said they didn't like math. But I'll be honest. When I was young, I didn't really like math that much. But let me tell you this about math. And this is something that as you get older, I think is one of the things that makes it one of the coolest subjects is in math, 1 + 1 =, tell me you don't like math. 2 + 2 =, and no matter how hard you try, 2 + 2 will never equal 5, right? Okay, so why is that important? Well, so many things in life are not so binary. They're not so right or wrong. But math, if you do it the right way, you will always come up with the same answer. And so it's not, as we in my family call it, gray, where it's not black or white, it's gray. Math is black or white, it's right or wrong. And so if you learn the techniques, each year it builds on the next and the next, and it actually can get easier, believe it or not. So if you are having trouble with math, and I was a kid who even in college had a little bit of trouble with math sometimes, uh, if you ask your teachers, don't be afraid. That is why they teach, because it's not to get rich. Am I right, teachers? We don't teach to get rich. No. They teach for that moment where somebody who's struggling goes, have you ever had that faith before where all of a sudden something clicks? Well, that's why they teach. So if you're struggling in math, like I on occasion struggled in math, don't let that bug you. Ask your teachers, and they are more than willing to help, okay? Will you promise me to do that? The one person that ran out of the room that said they didn't like math? Is that okay? Promise me? That's more than one person that answered back. But so you have to like math in order to be a meteorologist. You have to like science. How many of y'all like science? That's a lot. That's great. So if you like science, one of the things you have to do to be a great scientist is you have to ask good questions. And we will have time for questions. I promise that. So you have to ask good questions because so much of science is trying to understand the world around us. And the way we understand anything is by asking questions. So you have to like math, you have to like science, and then the third thing in order to be a meteorologist you have to like is you have to like the weather because you're going to be talking about it all the time and forecasting it. And so I became a meteorologist because I was scared to death of tornadoes. How many of y'all don't like tornadoes out of curiosity? I see a couple of your teachers, and that's okay. I still don't like tornadoes. Um, but when I was small, and I was probably 3 or 4, I was really scared of them. I was scared of them because we lived across the street from tornado sirens. Now, do y'all have tornado sirens here in Red Bay? You do? Okay. So the tornado siren was closer than from me. Look in the back. You see that fire extinguisher in the back there by the door? So my bedroom was closer than that away from the tornado siren in my part of town. So all I knew is when I was really, really young, that all of a sudden that thing would start screaming noise and we'd run in the basement and we'd hide from these things that could kill us. Great. And so that made me really, really scared of the sound because it was loud and noisy. And then we'd run in the basement and we'd hide down there with all the bugs. There weren't that many bugs. My mom would swear if she's watching this. I promise there weren't that many bugs, but there were some bugs. And it kind of smelled damp and it was dark and I didn't like it. And so I became very scared of tornadoes. And so then what my parents did is what I think we should do with anything that we're scared of. We learn more about it and we find out that it maybe isn't as scary as we thought. And so my parents, they went to something called the encyclopedia, which is basically the internet in book form. So it took up a lot of space then, but obviously has less information than the internet. And so they gave me encyclopedias, and I would read information about how tornadoes form, where they formed. I grew up in Kansas, so kind of like Mississippi, we had a lot of tornadoes in Kansas. And so as I learned more and more about tornadoes, I realized that they're actually pretty rare. I mean, we have them a few chances every year in this part of the country, but most of the time, they're luckily don't hit and hurt people. Sometimes they do. But I learned that how rare they were. I started learning how they form. And ultimately, what started off as a fear became a passion to learn more about it. And ultimately, is the reason why I'm a meteorologist today. So if there's something you're scared of, maybe it's weather related, maybe it's not, talk to an adult about that. And they might be able to help calm those fears and give you information so you can learn why there's really not anything to be scared of related to that at all. So just something to keep in mind. But for me, that's how I became a meteorologist. And so in order to become a meteorologist, you have to go to college for 4 years, like many of your teachers. So some of them probably gone for 6 when they get their master's and upper level sort of education. So for meteorology, you have to go for 4 years. And so I went to the University of Kansas. Again, Kansas is one of those square states in the middle of the country. And I spent 7 years in Texas before moving here to Mississippi almost 15 years ago. And it's certainly been a wild ride, and I've had a great time with it. And so it's been a good career, but so much of what I do is try to forecast the weather. How many of y'all have made a weather forecast before? I see some shorts there. I see some jeans. If you looked out the window at any point today and decided, oh, I'm going to be hot if I wear those long pants, or I'm going to be cold if I don't wear long pants, then you made what's called a nowcast. And that's a forecast for right now. And so a nowcast is the most basic type of forecast. Now, but every single one of you, before you go out to recess or went out to recess today, made an assessment. Do I need my jacket or not? Or are you standing below this big vent and is it cold? Should I move over here? I now casted that it's less cold over here than it is right there. So each and every one of you have made a forecast for right now. And a large part of my job that people know me for is doing just that, which is looking at where thunderstorms are, where the rotation is, where could a tornado form, and where is it going. And believe it or not, any one of you could probably do that with just a little bit of training. You might actually be very good at it. In fact, probable that somebody in here, maybe even likely, could be better at it than I am. Maybe one day we'll work together. Anybody y'all want to be a meteorologist when you grow up? Okay, we have quite a few. So odds are pretty good that there's at least a few of you that'll be smarter than I am right now by the time you get to my age, and probably a lot better looking. And so we might have my replacement in here. Hopefully, that's the case someday. Um, so, forecasting, the way we forecast the weather is we try to take lots of information, and there's almost too much information, and boil it down into what could happen right now, like y'all do when you look out the window and say, oh, it's sunny and it looks a little warm. So I'm going to go out there and assume I don't need my jacket. We start at that point with a nowcast, and then we build through a short term and then a long term forecast. And the way we do that is we start using better and better information from typically longer distances away. So we might look at in the short term forecast, we're looking at, what we call a radar, which is a beam of energy that's sent out from a rotating dish. And as it hits something, it says, hey, there's something right there and something right there. But there's nothing right there. And the more it reflects back the energy, that's how we find out where thunderstorms are. So just if you've ever watched, how many of y'all seen the radar when we're doing the weather and it's that big red blob and it's got some green and yellow and it's doing something? Well, so when you see the big red blob or where it looks bright or bad or however you want to describe it, the reason it looks like that is it's just very reflective. It's not necessarily bad. There's just a lot of something there. And typically, if it's reflecting back a lot, it's usually pretty dense. There's a lot in there. And so it might be a ton of raindrops. There might be ice that's reflecting back more strongly. So there'd be hail that's falling in that case. And sometimes when storms have hit, say, buildings, like a tornado hits something and causes that damage to be lofted, that reflects back very brightly too. So sometimes it's bad, but sometimes it's just a ton of rainfall. And so we use that data to try to determine where rainfall is going, where storms are going, and then extrapolate or forecast out in the short term where those will move. We use satellite. We have these temperature and moisture measuring equipment all around the country, and we aggregate, we put that all together to help make the forecast for now, for the next few hours. And then all that is done. Remember, I said you needed math? Goes through computers and it's processed, and that's how we end up making our forecast through what's called a forecast model. Now, how many of y'all have ever seen a model airplane, a model car, or something like that before? If you've ever had one of those little Hot Wheels cars, you've seen a model car. And that means you can own a Lamborghini for about 50 cents, or they're a little more expensive than that now, but you probably get one at a secondhand sale for that price. And so if you take that little car and blow it up to full car size, there's going to be huge differences. The wheels will be misproportioned. There'll be giant chunks of it missing. It certainly won't roll and move the way you expect it to. And that's kind of what happens when we forecast the weather. If you've ever wondered, why is the weatherman always wrong and keeps getting paid? Thankfully, keeps getting paid. It's a good thing. But the reason when we make a mistake is because we forecast off of that model. And typically, what we're looking at on the screen, we might look at the United States in the size of a frisbee, as opposed to the United States, which is thousands of miles wide. So the difference between looking at on small scale and the resolution we have and blowing it up to a large scale, a lot of times is where when we miss something, and I have never had a completely perfect forecast, and I never will. I've got some 99% out there before. We've gotten almost everything right, but there's no such thing as perfect when you're forecasting the weather. And so when you blow it up to full scale, it's those little differences between what it looked like here and what it looks like in the real world that a lot of times the difference between it rained over your house and it didn't over yours. Sorry, I'm so sorry. Does that make sense? Okay, now, do y'all have any questions? So I want to leave tons of time for questions because I'm really good at talking and can talk for almost ever. But I want to know what you guys are interested in. So, teachers, if you will help me out, you all know who's listening. You've got your eyes watching them. Can you help just yell out some students' name, point at them, and we will get their questions? Y'all ready to help me with that, teachers? Is that okay? Okay. So, one of y'all just grab my attention on teachers, and I will go with those questions. Okay. So, right here. So, what is your question, sir? How do tornadoes form? That's a great question, an important question. So, would you believe we have a very good idea, but we don't know for sure on certain components on why tornadoes form? We can very accurately say that most tornadoes come from what's called a supercell thunderstorm. A supercell thunderstorm is a special type of storm. You see, what we call an air mass thunderstorm, just a general thunderstorm, goes from a, oh, that's a cool cloud to a, oh my gosh, it's raining, it's loud, and everything, to, hey, where'd that storm go? In about 45 minutes, they go from to producing all the rainfall, and then the rain clogs it up and it falls apart in about 45 minutes. Because you've heard what goes up must come down, right? A supercell thunderstorm forms in a different way, but with similar ingredients. It keeps what's going up separate from what's coming down. So with a regular thunderstorm, what's going up is hot, humid, sticky air rising into the sky. And so as it rises, that humid air, water vapor, the gas form of water, eventually condenses and changes form from a gas to a liquid, and those liquid drops are what form the cloud. Tons and tons and tons of water droplets floating in the sky. And so if those keep rising, they eventually get to a point where they're no longer warmer than the environment around them, and they start coming back down. And that's when all the raindrops, all the droplets of water tend to coalesce and they fall together and then they fall as rainfall. And so ultimately, what's going up gets clogged up by what's coming down. So back to that supercell thunderstorm, everything going up stay separate from everything coming down because the whole thing's rotating. The updraft in it is rotating. And so that keeps all the parts of the thunderstorm somewhat separate so that you can keep what's going up separate from what's coming down. And that rotation is what allows a storm that on just a normal day, up, down 45 minutes, to last for hours at a time 3, 4, 5 hours. A single storm can move across hundreds of miles. And so that rotation that keeps everything clean from what's going up to what's coming down is what eventually can produce a tornado. So we need the ingredient list then for that specific type of supercell thunderstorm. And so we need hot, humid air, what we call unstable air, air that wants to rise quickly. Because either there's colder air aloft or there's just enough hot, humid air near the surface. We need lift to get it moving upward. That's why if you've ever watched the weather and like, what's the deal with the red L and the blue H and the weird lines? Okay, so all of that stuff is related to helping produce rainfall or thunderstorms or lift in particular. That second ingredient. First ingredient is unstable air or instability, sometimes we'll call it, or fuel, sometimes we'll call it. Second ingredient is lift, something to get the air rising. And sometimes just a hot enough day, it can do that. Other days, it takes one of those blue lines, one of those cold fronts coming in, kind of scooping the air and forcing it up. Like if you, no one here has seen a snow shovel before, but you've seen regular shovels. If you're digging with a regular shovel and the sand or the dirt is piling up on it as you're shoving it into the ground, that's what's happening to the air. As the shovel of air or that cold front is swooping through the atmosphere, it's lifting up the air, and that lift helps to get storms to go. All storms really need those two things: unstable air and then lift. The third component that's special to tornado producing thunderstorms, supercell thunderstorms, is what's called shear. And it's what makes the whole thing start spinning, right? Because the spin is where the tornado comes from. And so the shear is a difference in wind direction and wind speed from what's going on at the surface to what's going on way up there. So you might have wind at the surface that's out of the southeast, but if you go up 5, 8 miles in the air, which is where a thunderstorm is, they can be 10 miles high or greater. That wind direction might be out of the northwest. And that difference in wind direction is what we call directional shear. And it's one of the things that helps get the storm to rotate. So you need those three main ingredients. You need the instability, the fuel for thunderstorms. You need something to get the air going up and something to make the storm spin. If you have all three of those, we get a supercell thunderstorm. And then the question is, what makes one of those produce a tornado? Because we get those spinning storms all the time. And so there are a lot of research going to say why this specific storm produces a tornado, but this one doesn't. But it all comes down to having those supercell thunderstorms and having the wind just right and the unstable air all right in that. That's a good question. Really good question to start off with. Okay. Teachers, wave me down on one. Right here. Okay. What is your question, sir? Why are tornadoes made? So everything in weather comes down to the fact that the Earth is both heated by a thermonuclear reactor and cooling off because it's not heated by one at the exact same time. Now, you might ask, where's the thermonuclear reactor heating us right here, right now? It's that big glowing thing up in the sky, the sun, right? The sun, a nuclear reactor that's 93 million miles away, is heating half of the Earth during the day and not during the night. And so that difference between half of us are getting warmer at the same time, the half of us are getting cooler, and then we're making the whole thing spin, and then the poles aren't getting as much energy coming in, makes it to where there's a huge temperature difference, right? You go to the North Pole, it's cold. And if you go to the equator, it's hot. See, all of y'all know this. Well, if you make something that's hot here and cold there spin, and you only heat half of it at the same time, you're not heating the other, it makes a mess. It's all different. It's all mixed up. It's all jumbled up. And so, whether it's tornadoes or hurricanes or rainfall, everything in weather comes back to the fact that the Earth is just trying to make it the exact same temperature everywhere. And if you've ever had something you're trying to mix up, like say a brownie mix or some kind of a drink, right? If you're trying to mix up, you put like what is it, Kool-Aid in the container? How many of you like Kool-Aid? Is Kool-Aid still a thing? Okay. Okay. We didn't do Kool-Aid in my family very much with our kids, so I didn't know if everybody else did. Okay, good. So if you're mixing Kool-Aid, when you first put the powder in there, right? It is the clear water and then the red powder, and you got to mix it up. And the mixing process makes it to where it's all the same color. It's all mixed up. And that's all the Earth is trying to do when it produces tornadoes. It's just trying to mix it up and make everything the exact same temperature and amount of moisture everywhere. And that'll never happen. But the more violently there's a difference, the more likely are for that mixing to be a hurricane or a tornado or something along those lines. It's just the Earth trying to stir everything up. So, good question. Very good question. Okay. Okay, hold on. Okay. Who do we have? Okay. What's your question, ma'am? That's a great question. So when the weather person talks, how do we know where to point to when it's just the green screen? So at the TV station, or I guess it's not TV station, right? At the broadcast studio, I will have a monitor like this. And so if let's play pretend here for a second that, well, there's where my camera actually is. Y'all appreciate you watching. So if that's my camera watching me there, we have it set up where there are wires going to different TVs. I'll have a TV in front. I'll have a TV on the side and TV on this side, right? And so when I'm looking this way, I can see the TV just like what you're looking at home. And the weird part about that is when you point on TV, your arm goes the opposite direction from what you expect in the mirror, right? When you lift up your arm in the mirror, the person, or I guess you, your reflection in the mirror, lifts up the same arm, right? Same arm goes up. But on TV, when I lift up this arm, I'm looking at the TV and the arm goes the other direction because I'm looking at what you're looking at home, or else I couldn't read the words on the screen. So it takes a little while to get used to that, but I'm looking just at a TV right here, a TV right there, and TV right there. And so while I'm standing in front of a green screen, I'm looking over at the monitor and kind of pretending to look at the green screen. So the computer takes that green and it cuts it out and says, we don't want to look at that. We want to look at a graphic. We want to look at a radar. We want to look at a camera, anything like that. And so basically, I'm just looking at the exact same thing you guys are looking at home on different monitors kind of pretending to look at the green screen, if that makes sense. So, and hopefully pointing out something interesting. Okay, sir, what's your question? How do hurricanes form? That's a great question. Okay. So, whereas a tornado, a very violent rotating column of air caused by a thunderstorm extending to the ground, that's technically the definition of a tornado. And so, a tornado happens on a very, very small scale and it needs strong winds aloft. We talked about that third ingredient, right? We said we need the fuel, that instability to get the thunderstorm going. We need the lift to get the air going up. And then we need the shear. That shear comes from a river of air way, way up in the sky. Well, that river of air is called the jet stream. The jet stream helps get the whole storm rotating. If you talk about a hurricane, I don't like to be messed with. It's kind of a loner. It's kind of just wants to get out there and do its own thing. Just leave me alone. That's a hurricane. And so hurricanes do very well in the middle of the ocean where nobody's bothering them. And so in the middle of the ocean, there's a lot of water, right? Is there water in the ocean? I can't remember. Yeah. Okay. Okay. So you go in the middle of the ocean, lots of water, lots of warm water that helps get the storms going. And if there's nothing not to mess with it and there's enough hot water, a batch of thunderstorms might grow up 100 miles wide. And as it collapses, it kicks out cool air that starts more thunderstorms. And now it's 110 miles wide, then 150 miles wide as these storms blow up and collapse day after day. And if they get big enough, the fact that the earth is rotating will actually help that batch of thunderstorms start to spin. And if it stays over enough hot water, and if there's none of that shear we were talking about that helps make tornadoes, and it just doesn't get messed with, it gets bigger and bigger and bigger until it forms a hurricane. And that's why your biggest and strongest hurricanes are always over the ocean. Because as they start to make landfalls, they start to come over top of land, what happens is they run into friction. Y'all know what friction is, right? Friction. Well, if I do this with your hands real quick. If you push real hard while you're doing it, what do you feel? Does it get colder or warmer? Warmer, right? That's because the skin cells are rubbing against each other and they're causing friction. And so when air from a hurricane goes over land or trees or buildings or the beach, it causes friction. That friction slows it down, right? If we go back to this for a second, you're doing this, your hands aren't moving as fast as if you just went and you kept them just a little separate, right? You can move faster than if you're pushing on the other. And so same thing happens with the wind, where the wind goes faster where there's no friction and then slows down when it comes over top of land or mountains or whatever it's running into. And so hurricanes are stronger over the ocean when they're left alone and nothing's bugging them. And then they come on top of land and that friction starts slowing them down more and more and more until they fall apart. And sometimes if that friction is just a little bit different in some spots, we can still spin up tornadoes even out of a hurricane as well. So hurricanes want to be left alone, and they get stronger when they're left alone over hot water, and they get weaker when they go over either cold water or start hitting stuff. That weakens them a lot. So good question. Okay. Okay, what's your question, sir? How is lightning formed? So let's go back to what we just talked about kind of with friction, and that's not truly it, but essentially what happens is in a thunderstorm, you'll have ice crystals. And those ice crystals rubbing against each other will happen very quickly as they're moving with air that sometimes is going up at 150 miles per hour and coming down at just as fast. So that might be an interaction between those two. It's almost a change of close to 300 miles per hour in the thunderstorm with what's going up and what's coming back down. Now, not every thunderstorm is quite that fast, but that interaction, that difference there as ice is being moved around with the thunderstorm causes static electricity to build up. And a different type of friction has probably helped each and every one of you produce static electricity before, which means you guys know how to make lightning. Did you know that? You know how to make lightning. Mm-hmm. I guarantee you've done it to your little brother or sister, or they've done it to you. Because if you've ever walked barefoot on the car or in socks, I think technically you can do it too, on the carpet during wintertime and you just kind of shuffling your feet because you're tired and you go touch the doorknob and you get that zap. I'm talking about, right? That little, that you touch something, you get that little zap. Has that happened to you before? No? Well, you must have a lot more moisture here in Red Bay than I have in my house. But if you've ever had that static electricity before, where you do that, or you go down the slide on the playground and you hear that, and you grab your friend's hand to get up and you zap them. You know what I'm talking about? Has that ever happened to you before? Okay, so that static electricity is a much smaller scale of lightning. Because as you're sliding down the slide, you're causing the type of friction that's separating charge that then when you touch your friend's hand, you release that charge that you've built up. And so in a thunderstorm, that static electricity just happens on a much larger scale. The difference happens on a larger scale. And so once the difference in charge between the bottom of the thunderstorm and the ground is big enough, you get the lightning zap. And lightning forms as it tries to equalize what happened there. But the real question is not just where lightning comes from, but where does thunder come from? From lightning, right? Why? Why is thunder loud? Anybody have a guess as to why thunder is loud? Why thunder even happens in the first place? What's your guess? Yeah, so the reason thunder happens in the first place is because that lightning bolt, right? You have to have lightning. Lightning comes first and then thunder. You can't have thunder. You're not going to have thunder without lightning. And so the lightning bolt, as that static electricity occurs, a lightning bolt is 10 times hotter than the surface of the sun. 50,000 degrees is how hot a lightning bolt is. And so as that lightning bolt comes streaking through the atmosphere, it rapidly heats up the atmosphere and causes it to expand and then contract together. So that's why if you've ever heard the term a thunder clap, that's why. As the air expands and contracts, you get that clapping sound. Okay, one big clap for everybody in 3, 2, 1. Perfect. Okay, so have you ever noticed that the thunder is actually a little louder at night, or at least it seems that way? And I have to admit, I was an adult who already had his meteorology degree before I really thought this through. The reason thunder is louder at night is because the sound of thunder rumbles longer, right? You hear this in the middle of an afternoon, you might hear just one big boom and it kind of goes away. But at night, it's just kind of and just it goes on and on and on. Because thunder occurs because sound makes it to your eardrum because of vibrations in the atmosphere, because of vibrations in the air molecules. And as those air molecules, one touches the next, until they make it into your ear, that's how sound from my voice or thunder or your friend's voice makes it to your ear. And so at night, that thunder rattles longer because the atmosphere helps to act like a tunnel and bounce it around the sound more because the air is stable. So you might get that same loud pop from the thunder bouncing off of the atmosphere, bouncing off of trees, bouncing off of buildings. It just gets channeled and rumbles longer and longer and longer. And so that's why it always seems like thunder is louder at night, is because it bounces off of more things at that point. It doesn't just go up in the atmosphere. So that's a good question. Yes. Mhm. Okay, so if I were so let me think. So if I was in front of a green screen, would I be invisible? If I wear green, yes. So if I wear green on the green screen, I'd be invisible. We can make the screen any color we want. So I can do an augmented reality where I put the graphic next to me on screen. And so in my system, I have that set up as like kind of a fuchsia, almost her color of pink shirt there. And so the graphic is set up like that. So my system says everywhere I see that, when I cut that out, I want to put the graphic instead. And so, but we use green because I mean green's a great color. Don't get me wrong, but I like blue better. So what? We're live right now from Red Bay. Yeah. Yeah, I think we will at some point here. Hopefully, we got. We're going to keep the voting going for the game of the week. Y'all got this close, and considering you were up against Tupelo, that's an incredible like a population difference, and you guys did a great job. So I mean, almost were there. So yeah, yeah, absolutely. Okay, so we have not got a lot of the big kids back here. Um, okay, hold on. Everybody's pointing. Do we? Is this the right decision? Do I have some people? Oh man. Okay, hold on. Okay, so what is it? Okay, so the question was, and this is kind of a specific question, so we'll try to answer this, and it has to do with the way tornadoes move. Why did the 2013 El Reno tornado, which is one of the largest tornadoes on record, switch directions? And it had to do with how slow it was moving. So, tornadoes within the overall structure of a thunderstorm, like if a storm is static, a tornado would still move within where it's at because of the way the wind is curling around the thunderstorm. And so, in the case of any thunderstorm, the what's powering that tornado is what's called a rear flank downdraft. It's that hook echo. If you've ever watched us during severe weather, and you see we're almost always tracking a storm for a tornado that looks like kind of like a comma where it has something like curling around it. And so that RFE, that rear flank downdraft, curling around the backside, if the storm weren't moving, and in Oklahoma, storms don't move nearly as fast as here. Typically, if we're going to have a big tornado here, it's moving 50 or 60 miles per hour. Well, there they can get a big tornado that's moving 6 miles an hour. And so, if the storm's not moving in that case, the reason why the tornado changes directions is as that wind is curling around it, it's trying to cut off the unstable air from what's coming down out of a thunderstorm. And that interaction causes the tornado to eventually wrap around with rain and occlude. So, the quick answer on that is because of how slow the storm was moving, the occlusion of the tornado was occurring, and it moved within the general shape of the thunderstorm because the thunderstorm is moving so slowly. If it moving more quickly, it'd be a more predictable path. When it's moving slower, it's a less predictable path, if that makes sense. So, okay. Yes. Yes. So, how does a Doppler radar work? So, a Doppler radar, we mentioned a radar a minute ago, sends out a beam of energy and then it listens to see what it hit essentially. So there's a big dish and it spins 24 hours a day, 7 days a week. And I get dizzy really quickly, so I'm gonna have to stop after two spins, but it keeps going. And so it spins and scans low and higher, back low, higher, 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 low, high, as it's spinning around in a circle. And so what it does, it sends out a little beam of energy and then it listens to see how long it takes for that to come back, how much energy is returned. And so, based on that information, that pulse and the way it uses that information, we can determine where storms are. And so, we can also determine using something called the Doppler effect. I know, great name. Um, how the wind direction is changing with that. Have you ever, okay, so you've been next to the highway out there with mom and dad, hopefully, in the car, and you hear a big semi tractor trailer truck coming toward you, and it goes, have you noticed that change in pitch? Like it's getting higher, higher, lower as it goes away. That difference that you see there between it coming at you and that higher pitch and moving away from you and that lower pitch is the Doppler effect. And so that allows us to know that if a raindrop is coming toward us, it's kind of compressing, for lack of a better way to put it, that sound, the signal. And so that compression that's occurring there tells us that it's coming toward us. The expansion would tell us that it's moving away. And so that's how that different shift there, we can determine how it's moving. And then there's other information we can use to tell, are we looking at rainfall or hail or debris or different things like that? Just a lot of math, but it all comes back largely to that little shift that we see. So, good question. Okay. In the back there. Yeah. Point, point at which one? Okay. So, what is the first step to predict the weather? Get a thick skin because you're going to get it wrong. That's the reality of making any prediction, though, is you have to understand that failure will happen. And in the beginning, often. I mean, that's whether you're learning tennis, trying to play football, learning math, cooking, you're going to make mistakes. You should never fear making mistakes. The only mistake that's a really true mistake is just saying, I'm not good enough, I'm not trying. So the first step to making a forecast is realizing, okay, something in this is going to be wrong, and I'm just going to have to get over that because somebody's going to say, you're wrong. You're right, I was wrong. Oh well, I'll do better next time, and then do better next time. So get a thick enough skin to know that mistakes are just going to happen. And then once you get past that, 1,000 foot way to look at it, the first step that I do when I make a forecast is I look at yesterday's forecast. So I know how accurate was our thinking yesterday? Was my thought process on how everything was going to go correct yesterday? If it was, great. We start adjusting from there. If it wasn't, we back up and we figure out what we messed up yesterday to understand if our models are doing well in this pattern or not. And then from there, we just kind of look at current conditions, how again are our projections working, how good was our forecast, and then expand from there and look at where, in my opinion, typically I'll start with rainfall, where projections are putting rainfall, whether or not that again is accurate, what is what we expect. And so much of it is going back and calibrating and correcting it for what we expected. Again, humans will always make mistakes, and so do computers. So trying to figure out how large were my mistakes yesterday, or did we have a really good forecast? And then that thinking can translate forward. But so much of it is reflecting back on what we did wrong to begin with. So that's a good chunk of my forecast is spent. What did we get wrong? How does that compare to what I expected? Was my thinking sound or was I completely off base? And so then we look at those model projections from there, look and see what all the different ones come up with. And that's kind of how we generate the forecasts. That makes sense, kind of? But the biggest thing is don't be scared to make a mistake because you will. Be scared to not learn from your mistakes or to never make a mistake in the first place. So, okay. Okay. Yes. So, how do hurricanes move so fast? So, hurricanes typically are going to move when they're in their development phases early on very slowly, believe it or not. They might only move 5 or 10 or 15 miles an hour. And 15 miles per hour is a little faster than you and I can walk, but not a whole lot faster, right, than we could run. And so, hurricanes, when they really start their overall movement picking up speed, is when they're typically going through some of a transition, a weakening phase, where they're not just based at the surface in the middle of the ocean by themselves, but that jet stream of winds aloft is starting to pick them up and move them faster. Now, their wind speeds pick up more and more and more as they get over more and more unstable air. And if it's just um, it's like a group of yelling people, which you all know about. If one person starts talking, the next person has to talk louder to get over them, and the third person has to talk louder to get over top of them until everybody's just yelling, right? And so, in the case of a hurricane, the reason the winds get moving so quickly is the batch of thunderstorms grows so large that what we call the Coriolis force, no test on that, but anyway, helps because the rotation of the earth get it to spin. And if it gets left alone, it's going to spin faster and faster and faster as it's sucking in more unstable air and, yeah, just continue to do its thing. So as long as it's left alone, it might get up 150, 160 mile per hour winds. And if it runs into something or runs out of hot water, then it'll start to weaken and slowly spin down. So it never just spins up and immediately just stops. It has to, like your car, rev up and spin up and eventually slow back down. Okay. Do we have one back there that the teachers would approve? Are we good with this one? Okay. Okay, so let's see if we can do this. So the question is, what are isobars? And if you've ever watched one of our maps, anytime we say iso in weather, um, that means a line of constant. So you might have a line of constant pressure is what an isobar is, right? It's a bar of constant pressure. And then you have isotherm, line of constant temperature. And there's 6 to 7 different options there of um, different ISO lines that we probably use on a daily basis. So, ISO bars, ISO hip is a line of constant height. So there's just a bunch of those different ones that we end up using. So an ISO bar is a line of constant pressure. And so pressure, air flows from high pressure down to lower pressure. So does that work? Did we check that box? Okay. You're gonna, yeah, they asked me to say, they, they, they asked me to show 6, 7, but I looked at it and it's like, I slid that one in. Anyway, okay. Okay, go for it. Yeah. Hold on. What is it? Why am I here? That's a question I don't know if I've been asked very often, but it's a really good one. So the question is, why am I here? And I actually haven't done the thing now that you mentioned that, and I appreciate you asking that. So the reason why I do these school visits, I pointed out that fire extinguisher over there a minute ago, is because my dad was a fire inspector. And so his job was to go around the schools and inspect schools to make sure they were safe from fires. And y'all do fire drills, right? What's some other kind of drill you do here at the school? Any other kind of drill? Yeah, lockdown. Okay. Do y'all ever do tornado drills? Okay, so if you think back to when I was a kid, right? We did at my school then at that point, we did fire drills and tornado drills. So fire drills, that was my dad's thing. And I was scared to death of tornadoes. And so we did tornado drills. And so a big part of the reason do these school visits is because it's an opportunity for us to talk about the thing that scared me, tornadoes, and get you prepared and hopefully make you a little bit less scared of that thing that scared me as a kid. And so the thing I haven't done is we haven't talked about one of your tornado drills, and I need somebody to help. I need a volunteer for this, and then we can pull almost anyone on this. Look, front row, you've raised your hand like 7 times. You want to be my volunteer? Okay, come over here for a second. Okay, so what's your name? Emma. Okay, will you show me what you do when you have to do a tornado drill? Can you show me what you do? What you do? Okay, hold on. I'm gonna do it with you. Okay, you're down here like this. We'll get down real low like this. Okay, is this what we do in tornado drills? Go down like this. Okay. Now, have you ever wondered why is it we do that? Is it because the teachers think it looks funny? Is that the reason why? Why do you think we do that? To keep us safe. Because if you get down like this, right? You get down low, and we're covering our heads, right? Cover your heads up. Because what we're doing is we're trying to protect ourselves from debris. It's like there's a big thunderstorm, right? Thank you so much. Would everyone give them a hand? Good job. So here at school, you do tornado drills. How many of y'all have ever done a tornado drill at home? Hold on, put those hands down. How many of you have done a tornado drill at home before? Okay, well, that's great that a few of you have, right? So that's the reason I'm here to answer your question, is to ask you a favor. Would you please be willing to do a tornado drill at home with your mom and dad, your grandma and grandpa, or aunt and uncle today? And the reason I ask that is because there's really knowing where a tornado is great, but it does nothing to save your life. The only thing that can protect you from a tornado is knowing, is one coming, and where do we go? And so here at school, the where do we go is probably the hall. Is that accurate? We go to hall and we do the funny thing. We cover up our head. We protect our head from debris. We try to put something solid around it. At home, you actually have better equipment for that. You probably have either a bike helmet, some kind of batting cage helmet. You probably have a helmet, right, to protect your head because it's the part of your body that's hardest to fix. And so, if you can protect your head, if you can get to a safe place and you can hide out there until the tornado goes by, you're going to be okay. But what my, I guess, request, what I beg you of today, and thank you again for reminding me, is this. When you go home tonight, would you talk to your mom and dad or your grandma and grandpa, your aunt and uncle, whoever it is you live with? Would you talk to them and ask them where you go in case of a tornado? And if they don't know the answer, and that's okay, I'll tell you the answer that maybe you could tell them. And so, what you need to do is you want to look for someplace on the lowest floor. So, maybe that's the floor you walk into the house on. Maybe that's a basement if you're lucky enough to have that one. But something on the lowest floor that has no windows, that's not on an outside wall. So, something in the middle on the lowest floor. And you want to get underneath something sturdy if you can, or put on that helmet, wrap up yourself in blankets and pillows to protect yourself from flying debris, and then stay there until the threat has moved on. But we want to look for down low and in the middle. If you do those two things, a lot of times we'll be okay. Now, there's one exception to this rule, and this is something to keep in mind. If you live in a manufactured home, when there's a tornado, we need to get to someplace else. And so, what I would then ask you is talk to your mom and dad. Say, hey, that weather guy came. And today he said that if there's a chance for tornadoes, we need to probably go visit someone else. And so maybe it's make popcorn and go to grandma and grandpa's house because they do have a basement, or make a cake, or take a game and go to another friend's house. Because if you live in a mobile home, 360 days a year, that is just fine for the weather. But on the case of a tornado, most people that are hurt and die in tornadoes are hurt and die in mobile homes. And research tells us that the best thing you can do in that moment is get to someplace safer. And so, probably the best thing you can do is plan ahead and plan to go to a friend's house, or talk to your mom and dad about, hey, there's a chance for tornadoes. Can we go to grandma's house and play games and have ice cream? Hey, listen, it's a fruit. Say the weather guy says we're going to pick up ice cream and go to grandma and grandpa's house when there's tornadoes. As long as grandma and grandpa live in a sturdy structure, right? So, promise me, would everyone promise me this, that you'll talk to your mom and dad, your grandma and grandpa, your aunt and uncle, whoever it is you live with today, about where your tornado shelter is? Because as long as you do that, then to a certain extent inside, I can feel like what my dad did when he was trying to protect people from fires is kind of what I do with this, trying to protect people from bad weather. That makes sense? Okay. We can do more questions. Okay. 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 Do you want to do one more question? Okay. One more question. You get to pick who I'm doing on this, though. Okay. Okay. What is your question, ma'am? So, how are tornadoes made? You know, and we've talked a little bit about that, but I think it's important to review that for a second. They're made when you have the right ingredients. And that's the thing. If you miss one ingredient, you're not going to make a tornado, right? So if you want to make brownies, you have to have the brownie mix, and you have to have the oil. I think there's some water in there, and there's some eggs. I'm not a cook, but my wife makes brownies, and they're great brownies. And so if if you have to make brownies, you have to have the right ingredients. You miss one of the ingredients, you're not going to make brownies. And so you can have a ton of hot air in a thunderstorm and a ton of lift, but no shear, and you're not going to make a tornado. And you have a ton of the spin is there, but there's not enough of everything else. You're not going to make a tornado. Just like you can make one brownie, you make a whole pan of brownies if you have the right ingredients in the right amount. So in the case of tornadoes, we need that hot, humid air. We need something to get that air lifting, and then something to make the storm spin, what we call shear. When you get those three things, you get the right amount, our chance of tornadoes gets pretty good. So thank you all so much for having me come out and talk with you today. Very excited to be able to do that. Y'all wave one more time to folks at home. And again, thank you so much for having me. Good luck tonight at the ball game. I know y'all have a really good chance. So thank you for having me. Yeah, I'm gonna head over to Tap Ride here in a minute. Thank you all so much for watching here. I'm gonna go ahead and shut this down. But appreciate y'all for supporting us here, Mississippi Live Weather. Hopefully that was interesting and fun. And yeah, we'll talk to y'all later.